Hi, we are Group 10 and we are here to discuss vibration insulation analysis.
Vibration is a serious problem when it comes to machines as it can cause damage to the machine's parts that can eventually lead to its failure. Aside from the vibration itself, noise levels are also evident which are unpleasant to hear. Due to this, the vibration should be kept at a minimum for the machine to last longer, and in order to achieve this, passive isolation should take place to insulate the fragile equipment from unwanted vibrations through the use of isolators like rubber, felt, cork, or springs. By isolating the source of vibration, we were able to protect the machine from excessive vibrations and minimize the noise levels it produces. This solution is commonly applied to rotating machineries like the washing machine. A simple design model of a vibration insulation system is shown by the figure, where y of t is the displacement of the platform from its equilibrium position relative to a fixed frame of reference. U of t is the displacement of the plant floor from its equilibrium position, m is the mass of the platform and the equipment, k is the spring constant, and gamma is the damping coefficient of viscous damping.
We are going to answer problem number 3.
Plot the graphs of T sub r versus the dimensionless ratio omega over omega naught for zeta equal to 0.1, 0.5, 1, and 2. For what values of omega over omega naught is T sub r equal to 1? Explain why the graphs imply that it is desirable that the mountings have a low natural frequency in order to isolate the vibration source from the equipment platform, and that using low stiffness isolators is one way to achieve this. Problem number 3. Based from the graph, the transmissibility is equal to 1 when zeta is equal to 0 for the dimensionless ratio. A value for zeta closer to 0 for the dimensionless ratio will approach a value of T sub r equals to 1. It is desirable that the mountings have a low natural frequency in order to isolate the vibration source from the equipment platform, since the basic principle in vibration isolation is to make the natural frequency of the machine on its foundation as far below the excitation frequency as possible. In this way, low stiffness isolators will be effective to isolate the vibration source. Since the isolators are low stiff, the vibration of the source will be easily absorbed and will minimize or even remove the vibration felt on the platform. If high stiffness isolators will be used, then the excitation frequency of the machine will coincide with, let's say, a metallic spring isolator which raises its natural frequency, resulting to a vibrating platform which negate the purpose of isolators.
The general solution of the motion for the system is my plus gamma y is equal to ky is equal to gamma y plus ku. Thinking Taking place transform of equation and assuming zero initial conditions, we get quantity ms squared plus ys plus k ys quantity S is equal to quantity ys plus k u quantity S, whereas the transfer function t is equal to y quantity S all over u quantity S is equal to gamma z plus k all over ms squared plus ys plus k. And input S is equal to JW, so we could get the frequency response of the function. T is equal to k plus gamma JW all over k plus mw squared plus j gamma w, where r is equal to yw y all over all over n is the frequency ratio and zeta is the damping ratio. It describes the variation of the ratio of the maximum steady state amplitude of the system to the maximum amplitude of base excitation as a function of the excitation frequency. When we simplify it, we get y raised to 4 minus 17.84 r squared minus 99 is equal to 0. The solutions are r is equal to negative positive 4.7208 and negative 2.1078J. Since R is the ratio of the driving frequency of the natural frequency of the system, our negative and complex values of R is invalid. Therefore, our valid solution is R is equal to 4.7205. The plot below shows the transmissibility T against the frequency ratio R where zeta is equal to 0.2. Our next problem is problem number 2. Denote by G quantity IW the frequency response of equation 1, that is the ratio of the steady state response to the harmonic input. U quantity T is equal to AE. The transmissibility TR of the platform mounting system is then defined to be the corresponding gain function. TR is equal to absolute value of G quantity IW. Show that TR can be expressed as.
Problem number 2. We know that transmissibility T sub r is equal to f sub t over f naught. It is also equal to 1 over r squared minus 1 and x over y. Furthermore, the values of f sub t, or the transmitted force, and x, the maximum displacement, are also known, and they are as follows. The transmitted force is equivalent to x multiplied by the square root of k squared plus the quantity c multiplied by omega squared, and it will be known as E1. For the maximum displacement, it is equal to f naught over the square root of the quantity k minus m multiplied by omega squared plus the quantity c multiplied by omega squared. This will be known as equation 2. In addition to this, when we multiply the denominator of equation 2 to both of its sides, the value of f naught will be known, and it is shown below. The equation for f naught will be known as E3, and with E3, we have all we need to solve for the transmissibility. This is through substituting E1 and E3 to the formula for transmissibility. Remember that the formula for transmissibility is equivalent to f sub t all over f naught, and f sub t is E1 and f naught is E3. From this, we would come up with the following.
we notice that the numerator and denominator both have x, and they can cancel each other out. So we would be left with, this may seem different, and it is indeed different from the equation that we would need to express transmissibility as. However, we must remember that zeta is equals to z over c sub c, and gamma is equivalent to omega over omega naught, and omega naught is equivalent to the square root of k all over m. Through a series of operations, we would be left with. Now, we have solved the problem number 2. But you might wonder, since t sub r is equivalent to f sub t over f naught, and it is also equivalent to 1 over r squared minus 1 and x over y, are there any other ways to show that the transmissibility can be expressed as the needed equation? The answer is definitely. There are other ways other than the one shown above which can do as the problem requires.
The next problem is problem number 5.
For problem 5, we are asked to test the results of the design strategy for the situation described in problem 4 by performing several numerical simulations of equation 1 and problem 1, using various values of k as well as various input frequencies while holding the values of sigma fixed. For each simulations, plot the input u of t and the response y of t on the same set of coordinate axes. Similar to the equation in problem 1, u prime plus ku. For problem 5, we are asked to test the results of the design strategy. Similar to the equation in problem 1, differential equation of the system's motion, we have my double prime plus gamma y prime plus ky is equal to gamma u prime plus ku, which is our equation 1. Applying Laplace transform of equation, we have ms squared plus gamma s plus k y of s is equal to gamma s plus k u of s. Transfer function of the system, we have t is equal to y of s over u of s, which is also equal to gamma s plus k over ms squared plus gamma s plus k. Frequency response function, as s is equal to j omega, we can replace the equation to the transfer function of the system. Then we get t is equal to k plus j gamma omega over k minus m omega squared plus j gamma omega. Thus, we get the frequency response function as seen in equation 2. Given that sigma is the value of damping ratio and r is equal to omega over omega sub n is the frequency ratio, the equation 2 denotes the frequency response function wherein it interprets the variation of the ratio of the maximum amplitude of the system to the maximum amplitude of the base excitation where it functions as the excitation frequency. As the absolute value of y of t is equal to 0.1, absolute value u of t, we get absolute value of t of w is equal to 0.1. We can apply it to the equation 2 wherein we can get 0.1 is equal to square root of 1 plus 4 sigma squared r squared over square root of 1 minus r squared plus 4 sigma squared r squared. Solving the equation, we have r raised to 4 is equal to negative 17.84 r squared minus 99 is equal to 0. Then we have the value of r is equal to positive negative 4.7205 and positive negative 2.1078j. As the ratio of the driving frequency cannot have a value of negative and with a variable, therefore r is equal to 4.7205. Plotting the frequency ratio and the transmissibility or damping ratio, you can see the graph. Observing the graph, as the frequency of ratio approaches 0, the value of transmissibility also approaches or is close to 1, which interprets that the mounting should have a low frequency, so that the value of transmissibility is close to 1. Therefore, attaining low natural frequency would be possible with low stiffness isolators.
Our last problem is problem number 1.
Denote by y of t the displacement of the platform from its equilibrium position relative to a fixed frame of reference. Relative to the same fixed reference frame, let u of t represent the displacement of the plant floor from its equilibrium position. Show that the differential equation for the motion of the platform is y double prime plus 2 zeta omega naught y prime plus omega naught squared times y is equal to 2 zeta omega naught u prime plus omega naught squared times u, where omega naught is equal to the square root of k over m and zeta is equal to gamma over 2 times square root of m times k is a dimensionless parameter known as the viscous damping ratio. Problem number 1. Since the model includes forces and displacements, we consider Newton's second law of motion, F is equal to m times a. By assumption, the direction of displacement for both y of t and u of t are upward. Since the spring is always directed opposite to the displacement, then the spring coefficient k is directed downwards and the damping force gamma is directed downwards as well to oppose the direction of position. Then we have negative k quantity y minus u and negative gamma quantity y prime minus u prime, where y prime and u prime are velocities. Substituting these forces acting on the system to Newton's second law of motion, we will get the following equation. Since a is the second derivative of position, it is also equivalent to y double prime. Arranging the order of equation and removing the coefficient of y double prime, we have y double prime plus gamma over m times y prime plus k over m times y is equal to gamma over m times u prime plus k over m times u. Using the equations omega naught is equal to square root of k over m and zeta is equal to gamma over 2 times square root of m times k, we can solve for the constants gamma over m and k over m, in which we find that gamma over m is equivalent to 2 zeta omega naught and k over m is equivalent to omega naught squared. Then, we have the differential equation for the motion of the platform y double prime plus 2 zeta omega naught y prime plus omega naught squared times y is equal to 2 zeta omega naught u prime plus omega naught squared times u.
And that is for our vibration insulation analysis. Thank you for watching.